So now I'll do another deep thing, and what's amazing about physics done right, that every deep thing is in some sense trivial, but you just don't get it. We know that the way, from 18th century on, the way we construct the law is we say the law must obey the symmetries, which are, at that level there were self-evident symmetries. For example, at that time we gave up on the idea that Earth is the center of the universe and everything revolves in it. So we understood that there has to be a translational law, Newton's apple, that the same law that moves planet around sun, moves apple into your head. So the way you construct this Bayer action is you kind of enumerate all the symmetries. So when we produced the massive boson propagator, we said, look, I don't know which room I'm in, I don't know what's south, what's north, etc. It's all same to me, and that led to very unique and precise description for probability that I end up someplace given, and it just came from the symmetry, came from nothing else, and came from the idea that I don't care about anybody else. This thing became at most quadratic. And there is some parameter, I don't know, which is I have to measure, which is called either probability I will die in this room or the mass, Klein-Gordon mass of a scalar particle, depending on the physical problem. Symmetries are now constraints. They're really telling you there are things you're not allowed to do because of symmetry. For example, if I have translation symmetry, this thing cannot depend on the position, because that would break translation. If there was a Pope and Pope was in Rome and that was the center of the universe, I would not get that propagator that I wrote to you because there would be no translation invariance. So these are very strong constraints. What do? For example, when they teach you undergraduate quantum mechanics, about 80% of what they teach you is symmetries, but it has all kinds of funny notation, so you don't realize that. They're just teaching you translation and rotation group. It says in 3 dimension, my answer should not depend on direction. It should be the same every place. Nothing else. So that's why if you get Feynman as interpreted by Townsend course, you get Schrödinger equation as a consequence of translational symmetries. As a consequence of saying, I, Schrödinger, tell you this is the equation, and 103 years later, it's still the equation. So that's a translational symmetry in time. So now, so far, we did only one thing. We said, you can write this partition function, but because there is the law, they must obey Dyson-Schwinger equation. So now, to you it looks totally different, because when somebody teaches the Schrödinger equation, it's full of H's with cups on them, and bras and cats and M's and J's and all kinds of crap. But this equation that we wrote, which we call Dyson-Schwinger, it acted on this stuff here. It had to be expressed in terms of all corrections, etc. And it was really equivalent Schrödinger equation for quantum field theory, if you decide to put I's and H bars. So the simplest thing was translation. So how does that work? Now, I find it much easier to do it in this very general generating functional formalism. Because remember, this thing and those things, you can interpret them as generating functional as you want, or from them you can get endpoint correlations. There are many interpretations of the equation. But but this is the essence. Everything else comes out of it. And one thing will happen, and that's totally essential when you come, and that's why Feynman had to, Dirac and then Feynman had to introduce them. When you come to quantum field theory, it has Minkowski invariance, So it was very crucial that there was nothing special about time in these integrals. This is much more general than the Schrödinger equation. This is the mother of everything. And Schrödinger equation is chewing at the corner of it to get the computational scheme. So Schrödinger and all of the condensed matter is just a way of computing stuff, not necessarily deep, but this is deep. The symmetry is much simpler here, and the simplest version is called point transformations. So this, you will understand, you do actually know why we do the point here, because when we discretize the coordinate system on which fields are defined, that had two parts to it, always. It had some kind of function on the site itself, which in the most trivial case was, stopping probability or something. But the more general case is some nonlinear polynomial, the thing that shows up in a potential part of this action. And it's defined at every point. And then there was the other part, which was I had to explore my neighborhood even if I was alone. So that was obtained in the most local way possible. I only looked at what happens to my nearest neighbor, and that's coded into Laplacian. Laplacian is comparing what I'm doing compared to my neighbors. So that's the locality. But point transformations are very natural. And we'll see them in two ways. The first one is we could decide to change every coordinate in the same way. We define what I mean by the field phi, map it by some nonlinear function to some other field phi. That will be called a global or intrinsic transformation. Or what you can do is you can go to every point and give them slightly different rules. It's all allowed, but that's called a choice of gauge. If I tell you as I move from here to there, I change my German measuring stick from here to there. And that will be source of all our troubles. It will lead us to gauge theories which are ugly, horrible, and what nature chose. Electromagnetism is an example of that thing. But right now, let's just look at point transformations. What happens if I redefine the field? And let's do it very cautiously. When we have these fields, sometimes they are invariant under discrete symmetry. So for example, if this is called phi-4 theory, I'm allowed to change phi to minus phi, and the law doesn't change. So it's a symmetry of the system. It's discrete. It's big change, but nothing changes. Or I can have, this is a real number from minus to plus infinity. So I can map it into nearby real number by some functions. So I can say, let me go from here, a small coefficient. Be very cautious, make it as small as you want. And it's a set of functions, which if it's a point transformation, this function can look what everybody looks like and decide how to change local field. For example, in mean field theory, you find the natural coordinates for every field by averaging over everybody else, and you change coordinates that way, and then it's easier to solve your problem. So that's. Let's be cautious and change it by small amount. And then we like to take derivatives, Dyson-Schwinger equations, etc. Make this function at least once differentiable or something. But you know, in physics, you just make it smooth. Take as many derivatives as you want. We will only keep the leading one because we'll do this to the leading term. So now what happens to this integral? Remember, if you have n lattices, this is a little hypercube of n lattices, you know, going d1, d2, d5, 3, 4 to n of them. So this is a little hypercube. In Leibniz's way, you know, we make it as small as possible and make sure that integrals are well defined. So now my little hypercube gets deformed in different directions under this coordinate change. It gets deformed every place a little bit. So what I get is just still roughly the same volume, but a little bit different. And if I take epsilon to 0, it'll be identical, and if it's just a small deformation. This thing is just a volume. So what happens, this volume changes. And the way the volume changes is that it picks up a Jacobian of, that's my new integration variable here, you know, Ij, and then determinant of that quantity. That's the change of the volume, right? d phi I is mostly unchanged. So we will change the integral to phi prime. But we pay a price. The price is a Jacobian of the transformation. Now notice that on the left-hand side, this function only depends on j. It's some, you know, n-dimensional vector. This thing it knows nothing about. So, you know, this was a generating function and lots of chicken wires, etc. And this Fourier transform into Schwinger or somebody's representation, that's just our imagination. I mean, you know, nobody told us that this stuff has to be an integral or phi's. We just show that if we do this, you know, that's consistent. It's the same representation. So nothing here depends on phi. It's always an integral, but what will happen is this will change, and this will change, but j won't change. So left-hand side is invariant. So we have a huge group of symmetry, which is like what underpins general relativity. We are allowed to change every coordinate every place. So what we get here is epsilon. Variation of this thing. Take derivative with respect to all the values. And now to the order of epsilon square, you're allowed to change this to the new coordinate, evaluated in the new coordinate, etc., right? What's my Jacobian? Basically, you know, Ij is, the first term is just Kronecker delta, because nothing changed in the leading term. And then this term is a small parameter. And now this is a matrix with two indices, usually called Jacobian. Jacobi introduced it to describe what happens when you change coordinates nonlinearly. So this is a thing that has two indices. But I only care about determinant of this object, because only thing that I need to know at this level is the volume. I'm getting all my signs wrong, but it's correct in the book. If I take a determinant of object here, of this matrix, then it has Kronecker deltas on the diagonal. So the leading term is 1. And if you work a little bit, to keep only one epsilon in the expansion, all you're allowed is to keep only ones and one term when you're evaluating your proportional to epsilon. You're not allowed to have epsilon squares, etc. And that operation turns out to be trace. So now what happens is, in this path integral, I get the object with, sign plus or minus, doesn't matter, of trace of small change, infinitesimal change of coordinates, parameters by epsilon if I want to. So that's what's changed in the volume, but this stuff also depends on the field, so I also have to take derivatives of the action, right? So what happens to the action? Guess I don't need this stuff. The new variable, let's say phi prime, plus epsilon, the small change, the small change was this function, so it's fi, and then the first derivative of this thing. To make life easier, I stop at a linear term. So up here I get this plus something that's small. An exponential of something that's small is just 1 plus something that's small, so it's natural to put it down. And then here, I get that field plus epsilon something small multiplying j, and I just keep the next to leading term in epsilon. Now, nothing on the left-hand side depends on my choice of field coordinates. So the term proportional to epsilon has to be 0, because nothing depends on it. I'll just write the result, and then I'll use it to derive Dyson-Schwinger equation again, but this time as a consequence of symmetry and not just a consequence of fishing. So what happens is that when you collect terms in epsilon, you get d of action, d phi, this is a function of phi, but I know that I can put it outside by making this a derivative. So I'll write it in terms of derivative with respect to j. So it's going to be dj. And then, this guy created an extra term. So this will be plus ji. And this is multiplied by the coefficient of my epsilon, the leading term. So this is multiplied by whatever my deformation of the volume was, times field, but I am putting it outside of that thing. I also have this term that I cannot forget. So it's d phi, and that was a trace. Remember, I got a trace when I was doing it. So this is summed up here. Curly bracket, acting on my partition function of j. And the whole thing is 0, because nothing in partition function depends on our little epsilon that we were changing this thing. So now we get a weird new identity that you go ahead. I changed the volume, I changed the field, and I changed this function by keeping the first term in Taylor expansion, keeping the linear term in it. And change was epsilon times a non-trivial function, a function that I'd have you tell you what it is. For some reason, I like this function. Turns out there are infinitely many ways I can deform my whatever. I'm being sloppy. To leading order, it doesn't matter where I call it phi or phi prime. Yeah. That's number one. So I just did this to the volume, to the exponent. Then, because it's a small number, it's exponent on a small number. So I wrote it as 1 plus epsilon to whatever that was. That gave me this whole term. And the other term is coming from the volume change. So there are two things. One is just Jacobian according to Jacobi. I changed my coordinates. I went from Euclidean to cylindrical coordinates or whatever you want. Or I did some small deformation. This term, it's a trace of the variation of the field. So now, this is really like general relativity. There are infinitely many deformations I can do. I just have to make sure that they're small and they're differentiable, so I can do this thing. So I can change locally my coordinate by a point transformation any way I want. And for each change of coordinates, I get a constraint on the partition function. That's totally weird. There are infinitely many constraints on partition function. You say this function is a cosine of phi, and I say, well, then this has to be sine trace of sine something, right? So to guarantee that my partition function is unchanged by this fake integral here that we constructed. Remember, we got there by just taking Fourier transform, but could have done anything, right? So it says there are infinitely many path integral representations because there is no intrinsic coordinate system for these fields. We might find this natural or something else natural. So now, first application is trivial. It says, we shouldn't have spent a month fishing because we could have just written it immediately and that'll be done. And that's how, real books go. Professionals never tell you how they got it. They just tell you this is the answer and go screw yourself. But what could I do? I have this function, a vector, if I'm on n discretized sites of space-time. This is a vector whose index ran over n values. And it depends on the field. So let's say that this thing is a constant C. That's one possible change of it. What am I doing? I'm just translating the origin of phi. So I say, no, I don't want to say this is a zero field. I'll just raise it a little bit. That's good news because orbit Jacobian of translating the box doesn't change the box. It's obviously a symmetry of Euclidean space. This part is zero, etc. So we do that. So this becomes a constant, and this becomes a zero. So what did we get? The equation is J plus J of I acting on Z of J equals 0. But that's the first thing we ever found, right? That's Dyson-Schwinger equation. So, as its rule with naming things, it has name of two very smart young people. You know, they did it when they were in their teens or early 20s. Everybody knew it since, you know, late 18th century, but they got their name on it. And that happens to be Dyson-Schwinger equation for quantum field theory. So it's totally trivial, and the thing that we find most profound about quantum mechanics. But now it's for quantum field theory, because this representation is not just evolution in time, but anything that can happen in space-time in, you know, many dimensions. And the only thing that's added to this is, you know, we want symmetries and we want locality. And when you discretize the space, locality means I want to look at nearest neighbors. That's the best I can do. So that gives you what's called kinetic energy, Laplacian term, second derivatives, plus some potential. That's it. So it's total triviality. It just as trivial as Schrödinger equation. You know, this is deep, and Schrödinger equation is the same thing. I require that my Hamiltonian doesn't depend on time, so it's invariant at the time. You apply this, you get Schrödinger with I's and H's and, you know, whatever Greek letters you like. But that's all there is to it. There's nothing. So if we have perturbation theory to compute things, you know, this is helpful. But it's not necessarily the only way to solve the problem, and, you know, might be actually a stupid way to solve the problem. So what we showed is that this suggests that you solve the problem semi-classically by finding the classical backbone of your stuff, and that has nothing to do with, you know, either Schrödinger or Dyson-Schwinger. It's a deeper thing. So when you go to that island, that's what you remember. So everything we learned so far is embarrassing. I mean, just stuff we should have known in grade school. And Dr. Sherbakov's, he went to some amazing middle school where, you know, they knew everything already. It was in Kharkiv, and today it's a ruin thanks to the Russian fascists. But they learned him all, you know, they taught him all this already then, apparently. At least that's what he says. So now, this is a little bit more complicated. Can we get something more out of this? So now the question is, what is a symmetry? And the symmetry, you know, the basic idea of symmetry is that I do something to my law, and the law doesn't change its form. So, you know, this is a function of many, many variables, but it's just a number. And if I change the variables in a way that respects the symmetry of this number then doesn't change. So that's called invariance under symmetry transformation. If you do it for, you know, things like Dyson-Schwinger equation, then what happens at every lattice site, this is counting lattice size. This has to be satisfied every place, so it's a vector. So then the symmetry is something says that the law doesn't change shape even though coordinates have changed. So applied mathematicians call this equivariance. Physicists don't get what's the big deal, so we call it invariance. I mean, you know, so yes, if I take the derivative, then, you know, it changes according to the symmetry. What's the big deal? But mathematicians are slow, so they have to keep distinction. It's really not necessary. So now the symmetry is the following thing. If I have the law and I change it a little bit, the law itself doesn't change, which means that this guy has to be 0. So continuous symmetry is if you deform your coordinates a little bit in such a way that, for example, distances are preserved, so you're turning some radius or something, then you get a relation on the level of the law. The classical relation is that you have a little change of your law along coordinate I. So, the picture you have is something like that. I know it'll help you, but so you have a change, which is this guy, phi, I, of your position. This is your position in a space. This is the origin, and let's say this is a distance, or whatever you want to have preserved. And to make the distance preserved, you have to make sure that you're moving in orthogonal direction to it, infinitesimally. In other words, that my deformation locally at that point is such that I'm not changing the value of the action. Action is invariant. So the epsilon term has to be 0. So this is classical symmetry. So I was supposed to teach you that in the next spring, but much smarter person is going to do it. Lu Shi Wu, who is really smart, will teach that course. But she's very friendly to condensed matter people, so it might be helpful. So this is classical symmetry. Yeah?
Are you talking about the group theory class in the fall?
Yeah, I won't teach you. But you'll be in good hands. Much better than me. I mean, she's really something. You probably won't understand the thing, but that's your problem.
Wouldn't you
Yeah?
also want your volume change to be 0?
Yeah, so I have to, yes, I have to make sure that I don't get the trace term. So, in examples of like rotations, etc., we will check that that's true. But you're absolutely correct. This term, I have to make sure that it doesn't change. Well, it's doing the right thing. So I think I'm okay. It's satisfied automatically, I think. I think I'm okay without. So now, what's the quantum version of this? Well, you know what this thing is? That's called the first derivative. Well, okay, I'll just write it down and you can chew on it later. Acting on partition function equals 0. So remember, that just came from this equality, and we are keeping. So this is classical, and this is quantum. Now this J can be anything, right? So forget it. If I'm correct, am I correct? No, I'm sorry. This still depends on J. I have to keep it. So I told you, everything that has somebody's name was invented by somebody else. It's the same in positions, in sects, and stuff like that. It's goes without saying, all the good ideas are very simple, and they have For some reason, people like to give them names. So this thing is called word identity. Now, I like this particular naming because Ward was a very intelligent but independent spirit. So he was a sailor. He went to work on the transatlantic and oceanic ships as a sailor, carrying stuff around. And when he was, at Oxford, Cambridge, someplace, he derived the identities, these identities, quantum electrodynamics, and it turns they're very important to make sure that your calculations are correct. They take care of what happens in quantum electrodynamics is there are some, when you integrate this, there are things that are called fibers. They're like spaghetti. They're part of the integration which goes from minus to plus infinity in this infinite space where the action doesn't change. This is very bad because you multiply your integral by infinities, but they're boring infinities. Nothing happens to it. So what you do is you take a knife, you look at your bunch of spaghetti, you cut them. That's called base manifold. And you just evaluate everything. And the way you cut them, the French do it different than Italians, etc. That's called gauge fixing, gauge choice. And to make sure that everything is correct, no matter how you cut it, you have to use word identities. So they're very, very important. We'll use them. But for once, the guy who wrote the thing that was known since, it's not actually quite sure because lots of our understanding of geometry is from the 20th century. I mean, it starts with Lobachevsky and Minkowski, etc. in 19. But so maybe, this is already only 20, 30 years before he did it for physics. But anyway, they're important. And they're nothing. They're just things that says, when I change coordinates, I have to make sure that if I'm changing my coordinates in a way that is a symmetry of my classical law, the quantum law, the thing that has all the quantum corrections, has to make sure that it observes this relation. So this is a quartal version of the symmetry. So here we are. And, if you go to any reputable course, it doesn't look like this. Go ahead.
Explain from the time where that word identity comes from, like how does it?
What do you say?
How is that word identity derived?
Yeah, it's just derived by saying that product of this with the action equals 0. It says that this deformation doesn't change the action. On infinitesimal level, there is a little epsilon here. So it says, if I change my coordinates, like I rotate my fields that action is defined in, because I'm in Euclidean space or something, rotation is something that has to be orthogonal to my invariants. Like if you have a distance as invariant, phi should be something that's 90 degrees at it. That's what this means.
So
Yeah?
you're saying the first term and the third term.
Yeah, first term cancels this one. And what's left is the source term. And this one is the, I have to make sure, as you pointed out, that volume is conserved. This has to do with conservation of the volume when I do this transformation, right? That one came from volume conservation of the coordinates. So, I have to make sure this works. And there are very famous things in quantum physics where people forgot this term and wrote whole theories about it, and experimentalists found the phenomenon, etc. Eventually it just goes away because somebody says, but you forgot the Jacobian. Usually somebody from Russia does that because they're more careful about Jacobians. But they're in American particle physics, people have forgotten to check this term, and it costs you lots of money. Well, by that time they're tenured, so you can't do anything to them, but you never listen to them again. If they have forgotten Jacobians, sorry, I don't want to read your next paper. Life is too short for elementary errors.